Entropy change of an ideal gas. Two very useful equations for computing entropy. This relation was introduced in previous chapter. Can be developed for an ideal gas. TDS, for an ideal gas we have CV0 denotes the ideal gas, and we have PART8 relation. In this case, we use the first relation of Gibbs equation. ds du is CV0 dt, subtracting to t plus p on t dv. P on t equals to r on v we can make an integration. So we have this relation S2 minus S1 integration of for a constant volume we have this relation for a constant universal gas constant integration r dv on v. So we have L and V second on V1. R is the universal gas constant. Similarly, we can compute VTH. S2 minus S1 can be obtained as this relation. Minus R Ln on P1. So now we have two relations for entropy change. The first is R Ln V second on V1. constant pressure process. To make an integration to the relation, three possible methods are available. The first is a constant CP0 and CV0 available in tables. We can write this relation. CV0 for constant dt on T is ln T2 and for the second one we have also same relation as this expression. The second possibility for the specific heat B use an analytical equation for CP0 as a function of temperature. Temperature T, or we can write CP0 a function of temperature for example one those listed in table A6. The third possibility is to integrate. In this case we can write this relation, the relation for the S2 minus S1 as a function, as integration of a function of T. The third possibility is to integrate the result of calculation of a statistical from references temperature. Let me write the next page. C the third possibility is integrate the result of the calculation statistical thermodynamics. From reference temperature T0. To any other temperature T and defined as standard entropy. Standard entropy. So we have this relation S0T standard on entropy equals to the integration from the reference temperature T0 to the desired temperature Cp0 on T dt. This function can be tabulated in single entry ideal gas table as for the table A7. A7 or F5, or for other gases, for air, other gases, we have A8 table. A8. The entropy change between any two state 1 and state 2 is named. So entropy change any state 1 and 2 is RLN on P1. As with the energy function discussed in the previous section, the ideal gas table, tables A7 and A8, would give the most accurate result. The most accurate results and the equation listed in table A6 would give a closed empirical approximation, and the second accurate is for functions at table A6. Constant specific heat would be less accurate, except for monoatomic gases and for other gases below room temperature. Again, it should be appropriate in any particular problems. Let us now consider the case of an ideal gas undergoing an isentropic process. Undergoing an isentropic a situation that is analyzed frequently. We conclude that the equations that express it as S integration for the constant pressure Cp, for example, on T is be right. minus R ln P with the left side of the equation equals to 0, then expresses the relation between the pressure and temperature at the initial and the final state. With the specific relation depending on the nature of a specific heat as a function of T. As this discusses following this equation, there are three possibilities to examine. Of these, the most accurate is third, that is the ideal gas table. The equations for using the standard entropy equation was the standard entropy at point 1 S0 T1 T second minus S0 T1 The following result can be obtained. As standard and difference between two standard minus R ln P second on P1. For the Cp constant for an ideal gas, we can calculate that and isentropy process we have S second for an isentropic process. Now we can obtain this relation ln over T second R on Cp0. We can have also a relation for R on Cp0. R is Cp minus Cp on K. So for isentropic constant specific heat, we have this relation. Where K is 0 on Cv0. For an ideal gas also we have we can write the relation for P equals to R T on V. So P1 R T1 on V1 P second R T2 on V2. Substituting to this relation, we can write the equation for and from this last expression, we know that for this process equals to constant. For an isentropic process, K equals to constant P. The next section is the reversible polytropic process for an ideal gas.